Welcome to video number 2 for chapter 2, and we're just going to continue right along where we left off. So our last slide was number 7, so we're just going to continue on with our slides in order. Okay, so what this table is it's straight out of the textbook, first of all, and it is a table of prefixes. And what a prefix is a multiplier, okay? So in the metric system, everything is multiplied by tens. And we have common units, things like kilograms or grams or milligrams. And what that kilo is a prefix, and the milli is a prefix, okay? That tells us what to multiply our grams by in order to get bigger or smaller units. So what we're going to do is we're going to ask you all to have memorized 4 of these, okay? It's useful to have the entire table in your head, and there are loads of mnemonics that help you to do that. But for the purposes of this course, we want you to know kilo, deci, centi, and milli, okay? You need to have those in your head for exam time. All right. Now, I want to give you a little bit of tips and tricks on how to use this table, because it's really common for students to get things mixed up in their head as far as which way things go. So the easiest way, eventually we're going to get into converting things, all right? But the easiest way is if I'm doing something with, let's say I want to go from kilograms to grams, okay? Grams is the base unit. Okay, so what I'm going to do is I'm going to find the kilo on the table, and I'm going to put a 1 right there next to the kilo. I'm going to put the base unit right there, 1 kilogram. And then I'm going to come over here to the multiplier just to the right where it says 10 to the 3. I'm going to put that right there. Okay, so if I want to convert kilograms to grams, what I'm going to say is 1 kilogram equals 10 to the 3 grams. Okay, and I can do that with just about anything. So if I erase this business, and let's say I want to go from liters to milliliters. Okay, so notice that milli, that's a prefix. Okay, so I'm going to come down and find milli, and it's right there. So I'm going to say 1 milliliter is 10 to the minus 3 liters. Okay, because liters is the base unit. Milli is a prefix. Okay, so whenever you need to use this table or use those multipliers, this is an easy way to put things on there for practice so you can get used to using this. Okay, so let's take a look at our next slide, number 8. Okay, so 1 microliter, right? So this little funny symbol is the symbol for micro. Okay, we come back and come up and find it. It's right there in our table. Okay, so 1 microliter equals how many liters? So let's come up and take a look at our table. And I'm going to erase all this extra stuff so that we can see. All right, so let's find micro on the table, and it's right. Helps if I use the pencil. It's right there. So I'm going to say 1 microliter is 10 to the minus 6 liters. Okay, so that's where we're going to put right there. It's 10 to the minus 6, or we can say 1 times 10 to the minus 6 liters. Let's take a look at the next one. So just as a reminder, whenever we get to these numbered slides, where you have to do a problem, I want you to pause the video, try to work it out yourself, and then press play and see if you got it right. All right, so grams to micrograms. Okay, so if I look back on the table, so again, we're looking at micro. So we say 1 microgram equals 10 to the minus 6 grams, right? Okay, so we figured out that 1 microgram equals 10 to the minus 6 grams, right? But the question is asking us to go the other way. So if I flip it around, then it becomes 1 gram equals 10 to the 6 micrograms, okay? Because micrograms, these are smaller, right? So there's 1,000,000 micrograms in every 1 gram. Okay, and that's kind of how this table works. So if we come back and look at it, our base unit, this is where the base unit lives. So if we go this direction, we get bigger. And if we go this direction, we get smaller. Okay, so centi, milli, micro, nano, pico, right? So when you get down to nano and pico, you're talking about like the distances between atoms. Okay, so very, very small. All right. So now our next topic that we want to talk about is measurement precision. Okay, so how precise are our measurements? And it all depends on the measuring tool that we're using. Okay, so when we talk about how precise our measurements are, when we report those numbers, we say the measurement that we're sure of, okay, and then we estimate one more digit. Right, so let's look at my crude drawing here, and let's say I've got a ruler and some piece of wood that I'm trying to measure. How long is this piece of wood? Okay, so when we look at this, so we've got measurements at 1 inch, 2 inch, 3 inch, 4 inches. And then we can see that there's half-inch marks in there as well. Right, so I know for sure, let's do this in red. I know for sure that we are 2 inches, right? This is for sure that we're at least 2 inches. Okay, so when I say for sure, that's what we're talking about right here, this part of how we report our measurements. I know for sure that that's at least 2 inches. And then I estimate, let's say, so if that's 0.5 in the middle, I'm going to estimate that that's like 2.2, right? So that 0.2 is the estimate, right? Now the reason that we want to talk about this is, let's say I showed you this picture and I asked you to tell me how long is that piece of wood. You're not likely to say 2.25679. Okay, because there's no way that you can know that many digits. Okay, so for the tool that we have, the best that we can reasonably report it is one estimated digit. Okay, and it all depends on how many markings you have on your ruler. So let's say I add some more markings to my ruler. Right? So now I know for sure that it's 2.2, right? because it looks like it's right over top of that 2.2 mark. So I know for sure it's 2.2, and then I'm going to estimate one more digit. And if it's right on there, I can say 2.20 perhaps. And that 0 becomes my estimated, estimated digit. Okay? So measurements, we have to be reasonable about how accurate we can be. All right, I'm not going to report more than 2.20 unless I have more markings on my ruler. Okay, so let's take a look at an example of that. So I'm going to zoom in here a little bit, and we want to estimate, so we want to report this as accurately as possible. All right, so let's take a look. So we've got 30 is here and 20 is here. So each one of those lines represents 1 milliliter. All right, so if we look at that, so 20, there's 1, 2, 3, 4, that looks like it's at 25. Right, so we are sure of 25 milliliters. So now we're going to guess or estimate one more digit. And we want, when we take measurements from a graduated cylinder, we always want to measure from the bottom of the curve. All right, the curve is called the meniscus. So where does the bottom of that curve live? Right, it's just a hair above 25, right? So I could say maybe 25.1, 25.2, probably not 25.3. Right? So I'm going to guess, I'm going to estimate one more digit and say 25.1 milliliters. Okay? 25 is for sure. The 0.1 is a guess. Okay? I'm not going to be able to say 25.10 or 25.12 because I don't have the markings to be sure of any more digits. All right, so if I have to go by this, I'm going to guess 25.1. Right, according to the slides, I am correct. Right now, the reason that we're talking about that is that in the example here, this 25.1, are all of the significant digits for that measurement. Okay? And how do we tell which digits are significant when we're just looking at numbers? Okay, so here are the rules for determining what digits are significant. Okay, so significant digits first are all non-zeros. Any number that's not a zero is a significant digit. Okay, zeros between non-zeros, so that's talking about like this 0 right between the 1 and the 5, are significant. And when we have a decimal place, any trailing zeros count as significant. Okay, on the other side of the equation, numbers that are never significant are beginning zeros. Okay, so any numbers, any zeros that are in front of our significant digits, those are never significant. Now, numbers that are zeros that might be significant are ones that are trailing zeros when we have no decimal point. So notice this 47 million kilograms doesn't have a decimal point there. So we could have all of those digits be significant, or it could just be the 47. We're not really sure. Okay, so we're going to try and use decimal places to make sure that we're clear about what digits are significant. Okay, now, exact numbers. There are some numbers out there that are considered exact, so they have no uncertainty to them. Okay, for example, 7 pennies. There's not 7.1 pennies, there's not 6.8 pennies. There are 7 whole pennies there. Okay, and with exact numbers, we consider those to have infinite significant digits. Digits. Okay, the more significant digits you have, the more exact your number is. Okay, so if you have infinite significant digits, then you have an exact number. Okay, so counting numbers, if you're counting the number of people in the room, or the number of cars in a parking lot, or the number of pens on your desk, or in the case that we'll get to later in the semester, the number of atoms in a piece of matter, or something like that. Counting numbers are exact. The other things that are exact are definitions. Okay, defined values, or we can say definitions. Okay, so there are exactly 1,000 milligrams in 1 gram. There are exactly 3 feet in 1 yard. Okay, those are definitions, and when we use those, we consider those to have infinite significant digits. All right, so let's do a little practice with identifying the number of significant digits in a given number. Okay, so thinking about our rules, so trailing zeros count, leading zeros don't count, and any non-zero does count, and any zero between a non-zero counts. Right? So looking at the number we have, so these zeros right here are leading zeros, so they don't count. Right? Let me change colors here to purple or something. Non-zeros count and trailing zeros count. All right, so there are 3 digits that count. All right, so we have what we'll say is 3 sig figs. Okay, because it's easier than writing out the entire word significant digits or significant figures. All right, so 3 sig figs for this one is our correct answer. Now, we're going to be applying various rules for significant digits when we do calculations. Okay, so there's one set of rules for doing addition and subtraction, and another set of rules for doing multiplication and division. Okay, so our rules for addition subtraction. Okay, so your final answer will have the same number of decimal places as the fewest decimal places in your data, okay, or the numbers that you're working with. All right, so let's take a look at an example of what that looks like. So if I take 2 numbers, say 5.94 plus 6.366, right? This number has 2 decimal places, that 0.94. This number has 3 decimal places, the 0.366. Okay, so when I punch those into the calculator, what it does is it spits out a number 12.306. Okay, so the rule says that my final answer will have the same decimal places as the fewest decimal places in my data. All right, so what I'm going to do is I'm going to look right here. All right, so that's my second decimal place. Right, so now I have to either round up or round down by looking at 1 digit to the right. Okay, just one digit. All right, we're not going to look more than one digit. Just find the place where you have to stop and look one digit to the right. Okay, and our rules for rounding, hopefully those are in your head from previous encounters with math. Anything 5 and higher, you round up, and anything 4 and lower, you round down. Okay, so a 6 means that we round up. So my final answer that I will report is 12.31. Okay, so I have 2 decimal places here because I have 2 decimal places there. All right, let's look at another example. So 9 minus 4.453. Right? 0 decimal places for that number. 3 decimal places for this number. When I punch that into the calculator, the number that I get is 4.547. Okay, so my final answer has to have the same number of decimal places. 9 has no decimal places. So I'm going to stop right there, where I have no decimal places. Okay, so I'm going to use this number here to decide whether I round up or round down. So to correct sig figs, to correct significant digits, this number will be reported as 5. Okay? And it's all about certainty of measurement. So if I take multiple measurements, I have to include how sure I am of the accuracy of that measurement. And that's what significant digits is all about. Okay? So I'm going to erase this bit, and so we can talk about our multiplication division rule. All right, so our rule for multiplication division the final answer will have the same significant digits as the fewest sig figs in the problem or the data. Okay, so the numbers that you're working with. Right, so what does that look like? So if I have, for example, 15.972 times 6.2, right? This number has 5 sig figs. This number has 2 sig figs. Right, when I punch that into the calculator, I get a number that looks like 99.0264. Right, so I want to report a number that only has 2 significant digits. So that means that I stop right here, right, at that second 9. And I'm going to look one digit to the right to decide whether I round up or round down. So when I report the final answer, I'm going to report 99. All right, let's look at another example. Let's say I have 4.5 times 10 to the 3 divided by 6.644 times 10 to the 6. Okay, now we haven't talked about this yet, But when we look at scientific notation for sig figs, we just look at the coefficients, right? So the top number has 2 sig figs. The bottom number has 4 sig figs. All right, so my final answer is going to be 2 sig figs. So when I punch this into my calculator, the number that I get is 6.773028 times 10 to the minus 4. All right, so I want to cut this off at the second significant digit, and that's this 7 right there. All right, and then I'm going to look 1 digit to the right to decide whether to round up or round down. All right, so when I finally report this answer, what I'm going to report is 6.8 times 10 to the minus 4. All right, so let's go ahead and do some of these problems. And on second thought, I think I'm going to stop right here. I think I've gone long enough with this particular video. We'll come back in the next video and we'll continue with this work of using significant digits in calculations.